take the second derivative. Okay, what's the derivative of C1? 0. Here, 2C2, and that's it, right? Plus, okay, this one. 3C3 comes for the ride, 2 has to come down. So 6, right? I'm not going to write it as 6, though, intentionally. I'm going to write it as 2 times 3, C sub 3, x minus a what? To the 1, right? What's the next one? 3 times 4, which is 12. I understand that, but I'm not going to write that. X minus a squared. Plus, next one, 4 times 5 times c sub 5, x minus a to the third plus dot, 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 dot.
Is that where factorials come from?
Well, it's not where they come from, but you can see that they're being generated. It's actually that these patterns appear, and we had to come up with a notation to account for them. So the factorial notation accounts for the fact that they appear. All right. So how do I figure out what c sub 2 is? I'm going to do it on the side here for a second. What's f double prime of a? So it kills everything off except that. So 2c sub 2. So solve for c sub 2, and you get f double prime of a over 2 equals c sub 2. Yes? I think we need to go at least one more time. Let's take the third derivative. Maybe we'll go twice. Third derivative. No, sorry. Third derivative. So derivative of that is 0. Now look what happens here. This is all a constant. Derivative, that's 1, so we get 2 times 3c sub 3 plus, now check out, I think you're really going to see it now. 2 times 3 times 4 times c sub 4. 2 times 3 times 4 times c sub 4, x minus a to the first power. Plus, next one, 3 times 4 times 5, c sub 5, x minus a squared plus dot, dot, dot. So how do I figure out what c sub 3 is? I do f triple prime of a is, kills everything off except that, 2 times 3 c sub 3. Solve for c sub 3. I'll continue my list over here. The third derivative at a over 2 times 3 equals c sub 3. What's the next one going to be? Well, let me write the notation down just so we know it. How do you write fourth derivative? Because at some point you want to stop doing those prime marks. You write 4, close. Not that, that's incorrect. No? Parentheses around the 4. Okay? If you put just f4, like that means raise that function to the 4th power. 4 with the parentheses around it means take the 4th derivative. So when I do my 4th derivative, this goes away. What do I have? This right here, right? 2 times 3 times 4 times c sub 4 plus, and then I'm going to have more stuff, right? I'm not going to write any more down. So my 4th derivative at a should be 2 times 3 times 4 times c sub 4. So c sub 4 is the 4th derivative at a divided by 2 times 3 times 4. The 4th derivative at a divided by 2 times 3 times 4 is this. And is that enough for you to believe in the pattern? Okay. Now, I didn't put the 1s out here. 1, 1, you don't need them, right? 1. Anybody have a guess as to what the formula is, the general formula is for c sub n? Therefore, c sub n should be f nth derivative, right, at a over n factorial. Does that work for all the n's? Yes. because what happens if you try 0? You get the 0th derivative. What does the 0th derivative mean? Don't take the derivative, right? Okay, so that's the original function at a divided by 0 factorial, which is 1. So that's the original function divided by 1. We didn't see it, but there's a divided by 1. Now we plug in 1, take the first derivative at a, divide it by 1 factorial, which is 1. Second one, second derivative at a, divided by 2 factorial. Third one, third derivative at a, divided by 3 factorial. Fourth one, fourth derivative at a, divided by 4 factorial. Isn't that nice? We have a general formula for C sub n.
For every function?
For every function. You've just got to be able to differentiate it. Okay. That's the power of Taylor series, is that it works for pretty much everything that you can differentiate. All right. So this old formula for f of x, sum n equals 0 to infinity of c sub n x minus a to the n, we now know what that c sub n is. It's a formula. So this now becomes sum n equals 0 to infinity f nth derivative of f at a over n factorial x minus a to the nth power. There it is. That's the big formula for this section right there. This is called the Taylor series about a, or sometimes you'll hear centered at a. That's what a Taylor series is. Now, what is a Maclaurin series? Let me tell you. A Maclaurin series is Taylor series about the specific number 0. In other words, if somebody asks you for the Taylor series of a function, they must tell you what a is. But if someone asks you for the Maclaurin series of a function, it's implied that a is 0. So the best analogy I can make is, I can draw an infinite number of rectangles, right? But a square is a specific rectangle, isn't it? So a Maclaurin series is a specific Taylor series when a is 0. Otherwise, the Taylor is more general. Make sense? All right, time for you to do your first Taylor series. This is exciting. All right, I'm actually going to do Maclaurin series. We're going to do Maclaurins today. We'll do Taylor next time. Find the Maclaurin series for f of x equals sine x. So what I'm claiming here is that the function sine x from pre-cal can be written as a power series, as an infinite polynomial. And I want us to find what it is. Well, can you differentiate that function? Yes, and to do the Maclaurin series, I need to be able to take derivatives repeatedly. And I actually am looking forward to that because I know sine just keeps on oscillating back and forth between things. So I'm not too intimidated by this. So my goal right now is to try and figure out what those c sub n's look like, right? So I'm just going to start taking derivatives and then plugging in what to those derivatives? 0. Why 0? Because it's a Maclaurin series. So I'm always going to plug 0 into it, right? So I think the way I like to do this, you know what the function is, right? I like to just make a table. So I start out with the 0th derivative of the function, and I do it at x first. So just give me the derivative of this, or the 0th derivative of this function. It's just sine x, right? Now, go ahead and do the Maclaurin part, which means plug 0 into that. And what do you get? You get sine of 0, right? Sine of 0 is 0. Yes? Sine of 0 is 0. Remember, this number is c sub 0, isn't it?
Yes.
Okay. Now, let's do the first derivative, which is cosine x. And then let's take that first derivative and plug 0 into it. And cosine of 0 is 1. And so our constant, c sub 1, is 1. Then I take my second derivative, negative sine x. Because it's Maclaurin, that's not really going to matter, is it? Because when I plug 0 into that, I'm going to get 0. And that's going to be c sub 2. And then third derivative, negative cosine x. Plug in 0, and you get negative 1. That's my c sub 3. What's going to happen now? It's going to go back to 1, right? Or sorry, it's going to go back to 0. I'm going to start the pattern over, right? Now I'm only starting the pattern over because this is sine, right? Don't know why I put 5 there. Don't know why I put x there. So we're back to 0. And then it's going to be 1, 0, negative 1, 0, 1, 0, right? Negative 1, 0. It's going to continue that pattern. All right. Good. Because this pattern is so simple, what I'm going to do now is just start writing out the infinite polynomial. In other words, I'm going to take this general formula we have. Right? C sub 3 x minus a cubed plus dot, dot, dot. I'm just going to start writing this thing out. You ready? Remember what those were. So sine x is equal to c sub 0, which was 0, plus, shoot, hold on a second. I screwed this up. I'll admit mistakes. These are not your c sub 0, 1, 2, 3. Remember our formula for c sub n? It was the nth derivative at 0 over what? N factorial. What we got here were not the c's. I totally apologize. Just take the c's completely out of there, okay? Because that was wrong. Okay? Here, someone hit me. You want to hit me? You want to hit me? Somebody hit me? Flog me?
Did you use a bad word? Shoot.
I don't think I did cuss. I should cuss for that, but I'm not going to. Do y'all understand what we got there are these pieces? I left out the n factorials. Okay, let's keep going. So c sub 0 would be the first number off our list, right? Over 0 factorial, right? Yes? X to the 0. I'm using the formula. Let me put the formula up here again, even though I wrote it down. I'm using this formula. And instead of doing x minus a to the n, I'm doing x to the n because we're Maclaurin, so a was 0. Yes? Okay, that's the formula. This was more Taylor, but plugging in 0, we get that. Then plug in 1. What was the first number in our list, or second number in our list? Was it 1? Okay, so 1 over 1 factorial x to the first power. Okay. Plus, what was the third number in our list? 0. So 0 over 2 factorial x squared plus negative 1, good, over 3 factorial x cubed. Yeah? Okay, keep going. 0 over 4 factorial x to the 4th plus, it'll be 1. We're going back to 1 now. 1, 5 factorial x to the 5th. I'll do 2 more. 0 over 6 factorial x to the 6th plus negative 1 over 7 factorial x to the 7th plus dot, dot, dot. Yes? A bunch of those are zeros, aren't they? That's gone, that's gone, that's gone, that's gone. So this is just x, right? Yes? Well, you know what? Can you write that in sigma notation? Let me write it down first. We have 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus dot, dot, dot. Can you give that to me in sigma notation? What type of series is that? Alternating? Can you take care of the alternating right now? Negative 1 to the, well, where are we starting? 0? Negative 1 to the n should start us out positive. Because if I let n be 0, negative 1 to the 0 is 1. Then n is 1. That would give me a negative. So that should alternate the way I want, right? Positive, negative, positive, negative. Now let's try and pick up a pattern on the x's. Let's look at the x's first. This is x to the 1st, 3rd, 5th, 7th. 1, 3, 5, 7. Can you generate that list for me? 2n minus 1. So I have x to the 2n minus 1. We're using minus 1 because we want to start it at 0. Plus. We want to start it at 0 and get a 1 up there, right? So we've got the alternating part taken care of. We've got the powers on x taken care of. And now I just need these factorials. 1 factorial, 3 factorial, 5 factorial, 7 factorial. Odd numbers again, right? So I just need to create odd numbers. How about this? 1 over 2n plus 1 in parentheses factorial. How what? What do you mean? How long? How far to go? Yeah. Enough for you to be able to get the pattern. That's how far. Yeah, you need to be able to pick up the pattern. Make sense or no? Okay. Now, of course, like these are all numbers, right? This is like 1 over 6, 1 over something, 120 or something like that. Those are all just numbers in front. Yes? Do you notice anything about all those powers? I mean, we already kind of talked about it, but all these powers are odd, right? Do you remember in pre-cal, you were told that sine is an odd function? Do you understand now why it's an odd function? It's infinite polynomials, all odd powers of x. And thus it is odd. What were you told about cosine? What do you think is going to happen when we do this for cosine? We're going to get a bunch of even powers of x. How am I doing on time? 20 minutes? All right, let's do cosine, and let's do it fast. All right, f of x equals cosine x. We're going to do Maclaurin. Ready? The Maclaurin for cosine. So I'm start taking derivatives. Derivative, 0th derivative of this is itself. Plug in what? 0, cosine 0? 1, okay. Now take the first derivative, negative sine x. Plug in 0, 0. Take the second derivative, negative cosine x. Plug in 0, negative 1. One more, and it's going to start repeating, right? Third derivative is sine x. Plug in 0, 0. And now from here on, it's going to be 1, 0, negative 1, 0, right? And just keeps on repeating. So with that in mind, cosine x, do it up here because I want to write it up. I don't want to erase that yet because I know I wrote that really fast. Cosine x should be the first number we got, right? 1 over 0 factorial x to the 0. I'm using the formula again, right? Plus the next number we got, 0, over 1 factorial x to the first. And that's going to go away. Plus, next number, negative 1 over 2 factorial x, hey, even, squared. Right? Next one, 0 over 3 factorial x cubed, but that one's going to go away, so no odd piece, right? And then the fourth one will be back up here, right? So 1 over 4 factorial x to the fourth plus 0 over 5 factorial x to the fifth. Let's do one more. Negative 1 over 6 factorial x to the sixth plus dot, dot, dot. Let's kill off all the zeros and write out this nice series. So this is going to be, what's this? That's just 1, right? That's 1. This is gone. Actually, that's gone, that's gone, that's gone. All the odds are gone. This one is going to be negative, isn't it? So minus 1 over 2 factorial x squared plus, what's the next one? 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. What would the next one be? Plus 1 over 8 factorial x to the eighth. Right? Plus dot, dot, dot. Can you give me a formula for this one? It's alternating, starting what? Positive. So how about negative 1 to the n plus, no, just to the n. Oh, it starts the same way, doesn't it? Okay. Let's take care of the factorial part now. We have 1 over, this first one was over 0 factorial, wasn't it? So that's like 1 over 1. So 0, 2, 4, 6, 8. 2n factorial. Be careful when you write 2n factorial, it has to be 2n in parentheses factorial. It is not the same as this. That's not the same as this. So it has to be in the parentheses. And then what about the x? X to the 2n. Bam, there it is. There's your Maclaurin series for cosine. Even function. Pretty awesome, right? Now, let's not lose sight of something here. If you get on your calculator right now and you are in radian mode on your calculator, somebody get their calculator out real quick. It's out. Okay, just make sure you're in radian mode. Do cosine of 1 on your calculator and tell me what you get. Cosine of 1. 0.540 what? 30, something like that? Yeah. Okay. What I claim is that this is going to give you the same thing. So let's plug 1 in for x. So what would that be up there if I plug 1 in? 1 minus 1 over 2 factorial, that's 1/2, right? Plus 1 over 4 factorial. 4 factorial is 24 minus 1 over 6 factorial. I'm not quite sure what 6 factorial is. I think it's 120 times 6, 720, 720. Okay, plus dot, dot, dot. Now on your calculator, please, can you do 1 minus 1/2 plus 1/24 minus 1 720th? What do you get? Just, no, I want 1 minus 1/2 plus 1/24 minus 1 over 720. 5.40?
No, 0.5.
Point, this is approximately 0.5402 Okay, 7. So look, I stopped at the fourth one, right? And I'm pretty close to what your calculator got, right? How did your calculator get this? It computed the series out to a certain place. It has no idea what cosine is. It just did this. That's what your calculator did. All right? And it has a pre-built, like, programmed, whoever wrote the program in that, for that machine, right? Said, I will go out in this series to a certain predetermined tolerance and stop. And so there's in your menu, you can adjust how far out you want it to go. Like, you think your float, I think they call it the float, and you can adjust how far out you want it. And that will mess with the code and it'll take your series out further. But that's what your calculator is doing. It's using that power series. Okay, that's fun stuff. Let's do another one. I have 15 minutes. I think I'm going to have just enough time to squeeze this in. All right. What about for e to the x? What is the Maclaurin for e to the x? Isn't this kind of exciting? What are you already happy about here? The derivatives are all the same, aren't they? So the zeroth derivative of x is itself. And when I plug in 0 to this, because it's a Maclaurin, right? When I plug in 0, I get 1. And that's the way it's going to be the whole way, right? All the numbers that we get on top are always 1s. So that means when I start to write the power series out, if I follow the formula, it's the first number I get, 1, over 0 factorial x to the 0, plus the 1 again, right? Over 1 factorial x to the first, plus 1 again, right? 2 factorial x squared, plus 1 over 3 factorial x cubed, plus 1 over 4 factorial x to the fourth, right? You get the point, right? See, this is, the exponential function is neither even nor odd, right? Remember when you were studying even and odd functions, you could have neither. This is neither. It's not odd, it's not even. Does that kind of make sense why it's both? All right. Now, I'll do one more little thing here. This is 1 plus x plus 1 over 2 x squared plus 1 over 3 times 2 x cubed plus 1 over 4 times 3 times 2 x to the fourth plus 1 over 5 times 4 times 3 times 2 x to the fifth plus dot, dot, dot. I think I may have shown you this earlier in the semester. But check this out. It's so cool. If we take the derivative of this, what should we get? Itself, right? Take the derivative of this power series right now. Take the derivative of that power series. Let's see what happens. What's the derivative of 1? Derivative of x. Plus 2 comes out. Half of 2? 1 times x. Plus 3 comes out. 3 cancels, you're left with 1/2 x squared. Plus 4 comes out. 4's cancel. 1 over 3 times 2, right? X cubed. Next one, 5 comes out. 1 over 4 times 3 times 2, x to the fourth plus, and those are the exact same things. I just rewrote it, right? That's the exact same thing. It's the exact same expression. That's what e does. It is its own derivative. No other function behaves that way. All right, how about the sigma notation of this? What's the sigma notation that would give us this? I heard it. This in sigma notation should be sum n equals 0 to infinity. We always have 1 on top over n factorial x to the n. That is your Maclaurin series written in sigma notation for e to the x. It's exciting. All right, 10 minutes, I get to show you the most beautiful equation. Are you all ready for it? You are. You are ready. I know you're ready. All right, here's what I want to show. I'm going to try and prove to you right now that e to the I pi plus 1 is 0, right? That's what I'm going to try and prove to you? Yeah? Would you be satisfied if I could just show you this? Sorry, Laura, I'm going to disappoint you then. Yes, but that's the same thing, right? I'm not going to show this. I'm just going to show this. Is that all right? Okay. If I can prove to you that this is -1, then obviously -1 plus 1 is 0. That we won't debate about. All right, here we go. One more thing. I to the first power is I. What's I squared? This, you have to go back in college algebra, and the way we defined I squared should be -1. I is that special number that when you square it, you get a negative. Okay? What is I cubed? Well, that's I times I squared, isn't it? What's I squared? -1. What's -1 times I? Negative I, right? Okay, what's I to the fourth? Isn't that I squared times I squared? So isn't that -1 times -1? 1. What's I to the fifth? Well, isn't that I times I to the fourth? So isn't that just I? And what's going to start happening? It's going to start repeating. So we call this cyclic, okay? It's -1 does the same thing, right? -1 to different powers is going to cycle back and forth between -1, +1, -1, +1. I raised to different powers is going to cycle, but it's a 4-phase cycle. It's I -1, I 1. I -1, I 1, right? Keep that in mind. All right. Remember what I'm trying to show you. And 8 minutes. All right, what is e to the x? Written in its power series. 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus ... Right? We just did that? Okay. Then what is e to the I pi? Well, e to the I pi, this is my x, right? Okay, so this should be 1 plus I pi plus 1 over 2 factorial I pi squared plus 1 over 3 factorial I pi cubed. I'm going to keep going. 1 over 4 factorial I pi to the fourth. I need to go about 3 more. 1 over 5 factorial I pi to the fifth. 1 over 6 factorial I pi to the sixth. One more. 1 over 7 factorial I pi to the seventh. Plus ... Equals 1 plus I pi plus, let's go ahead and square this. When you square I, what do you get? -1, right? And then when you square pi, you just get pi squared. So here's how I'm going to write this. I'm actually going to take that plus away. I'm going to make it minus 1 over 2 factorial pi squared, right? The next one, what is I cubed? Negative I, right? Negative I. So watch how I write this. Minus 1 over 3 factorial. 1 over 3 factorial I pi cubed. Next one, I to the fourth. 1. So plus 1 over 4 factorial pi to the fourth. Next one, I to the fifth. I'm back to the beginning, right? So that's just going to give me I. So I'm going to have plus 1 over 5 factorial I pi to the fifth plus I to the sixth, -1. So negative 1 over 6 factorial pi to the sixth, I to the seventh. Where am I at? Negative I? Yes? Negative I, so minus 1 over 7 factorial, negative I, pi to the 7 plus dot, dot, dot. I know that looks like a disaster. 5 minutes. I would like to group things now. Do you agree with this? 1 minus 1 over 2 pi plus 1 over 4 pi. Not 4 pi. I'm writing this down wrong. 1 over, I mean to write this one. 1 over 2 factorial pi squared plus 1 over 4 factorial pi to the 4th minus 1 over 6 factorial pi to the 6th, and that's it, plus dot, dot, dot. Those are all the terms that do not have I in them. Plus all the terms that do have I in them. I pi minus 1 over 3 factorial pi cubed plus 1 over 5 factorial pi to the 5th. I have one more, minus 1 over 7 factorial pi to the 7th plus dot, dot, dot. Yes? What am I missing out of these? Hold on. I'm missing i's. I'm missing i's in all these. I, right? Yeah? Those all have i's, don't they? Let's factor an I out. Factor out this I, factor out that I, factor out that I, factor out that I, and let's just stick it out here because it would distribute through. Do you recognize this? Close? They're even powers. They're all even powers. Isn't this cosine? This is cosine of what, though? Cosine of pi. And do you recognize this? This is sine of pi, but then times I. What's sine of pi? 0. What's cosine of pi? Negative 1. We're done. Cosine of pi is negative 1.
And then the one at the beginning.
Well, didn't I just show you right now that e to the I pi is equal to cosine of pi, which is negative 1? Isn't that what I was trying to show you? That's pretty awesome. Okay. I'm going to give you the homework assignment for this section, but you're not going to be able to do it all, so I'm just going to give you a little piece of it. Just for those of you who are like a little ambitious. Page 487. For now, 5 through 10. And remember, my videos are online for homework solutions. And I still have a minute. I'm going to pass the sign-in sheet around. I know y'all want to go, but I have a